Thanks, Mike. Thanks for the introduction. Like you said, my name is Drake Hintz. I'm gonna be taking over as the acoustician here at PAC. And so if you haven't met me, send me an email. I'd love to meet you, set up a meeting, whatever it might be. Topic for today is basically how fire and sound, fire requirements and acoustic requirements play together. And you'll find they often don't play nicely together. So it takes some doing to make sure your project is meeting all the requirements you want to meet. This is an AIA accredited presentation. We've given it a number of times. So if you've seen it before, I might have a little bit of a different spin, but a lot of it might also just be some review for you. So just kind of as an overview of what we'll go through here, we'll start by going over some of the basics of acoustics, and then kind of the basics of the fire ratings. And then we'll go kind of this section we call the devil is in the details and really dive into each one, fire and acoustics. And then we'll kind of talk about how these things can lead to some tensions in the design teams and who's got different stakes and what, and how that plays out through a project. And you'll find there's a lot of rules of thumb that we use both in acoustics and in fire, and it can get you in some trouble in some places. So we'll talk about some of those and then go through examples and then have a Q&A session. And then, as Mike said, not written here is going to be the Ask Mike Anything after that. So yeah, kind of to start, acoustic requirements. This is a big one in the acoustic requirements field, and what you'll see a lot of manufacturers, including us, spend a lot of time thinking about is the multifamily requirements. The requirements for multifamily is a lab test of STC 50 or IIC 50, or a field test of NNIC 45 or NISR 45. So if you're not familiar with these metrics, it's airborne sound and impact sound, kind of the difference between like if you have an upstairs neighbor with a toddler thudding around, as I often do here in my own house, have a toddler thudding around upstairs. That's more impact, right? Or when you have a toddler screaming and crying, that's your airborne. Very real personal experiences for me right here, right now. But it can apply to many different things. So the NNIC is just a field version of these lab measured metrics. It's just a specific way to test it in field. Actually, we were just, as Mike kind of alluded to, we were up in Philadelphia at a conference presenting, and Jerry Lilly had a really cool presentation. If you aren't familiar with him, he's a important name in the acoustics world, and we all look up to him. But he talked about how NNIC, it was adopted in, I think, the 2021 code cycle. It used to just kind of be up to the acoustician of which field metric they want to use. Now it's kind of standardized. And kind of how we said some of these things can get us in trouble. There are certain situations where that's not measurable. You have a limit on NNIC and NISR of 150 cubic meters. And if you have a space bigger than that, you can't test these metrics. So kind of one of those fun little things that we do in acoustics, have to deal with some real world practicalities of what's in the code and what we are allowed to test. And Jerry Lilly had some really interesting thoughts about that. But I think kind of underlying all of this and these code requirements is they are, I think everyone in the acoustics world would agree, they're kind of frustratingly low requirements. And a large percentage of people, this is actually written here, a quote from the International Code Council, but the short of it is a large percentage of people would be highly annoyed by their neighbors at what is a code compliant level of noise isolation. So just one of those things to think about. And when you hear acousticians arguing for more acoustic mitigation, it's not just because they are being picky or needy. It's because they're trying to design spaces that everybody wants to be in, and that's something that we face as an industry quite often. So question, once upon a time, I think the first time this presentation was given, it was kind of more of an official poll, but here we can just use the chat kind of as a pseudo poll. What sources do you use to find your acoustically attested assemblies? There's a lot of them out there. We certainly have our own here at PAC. We publish our tests, and I know a lot of other manufacturers do as well. But if you have some source that you're excited and you think people need to know about, throw it in the chat and spread the word, because I think everybody wants more data. So that same code council, the ICC, put out another kind of supplemental guidelines for going above code minimum, and they released what they would call like their grade B acceptable performance, and then preferred performance grade A. And then you can see those numbers here. I won't read them all out to you, but it's basically an additional 5 points for each one above code minimum. And I think it's kind of funny, like they obviously put out a statement where they're like a large percentage of people would be annoyed at code minimum. And then they released something above that is acceptable performance. So if you achieve acceptable performance, but code minimum is below acceptable, what does that say about our code? And it's not surprising in that case that people would be annoyed at code minimum. So just kind of, you know, the code council is aware. It's not just us acousticians being needy again. So basics of fire rating. You often see these fire ratings listed on drawings and on different assemblies and like your partition sheets and drawings and stuff like that. And you see it as 1 hour, 2 hour, 3 hour, and it can go up. And there's some odd ones in there as well that fall in like the half hours and weird stuff. But what do those ratings mean? We often talk about in acoustics, we don't like the word soundproof because it's all very relative. And if you have enough sound, it will get through anything. So soundproof isn't a fun word in the acoustics world. And I think similarly, fireproof isn't exactly what we're trying to get at with these ratings. Basically, what the rating is trying to get at is how long will the structure be intact with a fire in the space, right? And so when you're designing to these different fire ratings, a lot of things have to go into it, like what are the exit paths and how far away are occupants to your exits, and how tall is your building, and how long does it take for your firefighters to get to your building to start treating the fire. And I'm no fire designer. I'm on the acoustic side of things, but from my understanding, that's what those requirements come from, and I'm sure there's a lot of interesting conversations that go into what the criteria are and requirements. But yeah, that's kind of what those numbers are getting at. So similar question here for fire. Where do you find your fire rated assembly types? Some of the ones we're aware of, this GA design manual, the UL listings, then the ICC ESR reports, and manufacturers publish their tests and their UL assemblies as well. We do certainly here at PAC. Do you have any others that you guys are aware of? Throw them in the chat. So basics of fire testing. Fire testing is kind of a whole thing, right? So as I've mentioned, I came from the acoustic side, and we have a whole system behind how we test acoustics, which I was very aware of as a consultant. And there's differences for how you test in the lab and in the field. What I was less familiar with was fire testing, and what I'm learning at least is it's similarly involved, similar level of complexity, thanks, to the fire testing as there is to the acoustical testing. So when you go to test a fire rated assembly, you have to build the entire assembly in a lab. And you basically have, like in acoustics, you have a source side and a receiver side. So you have a lot of noise in one room, and you measure how loud it is both in the source room and the receiver room, and you get some difference, and that's broad strokes. That's how you get your acoustic ratings. In fire, you have a similar thing where you build your whole assembly and you start a fire in your source sound, like the analogous room to your source room. And then you do a couple things on during this test, and there's 4 different ways to fail basically a fire test. And the first is passage of flames. This seems pretty obvious. If your fire is going down in that source room and you're looking on the receiver side and you see flames entering that room, that's a failure, and that's pretty obvious. If you're in that room in the real world, you would say that you're exposed to fire, and so therefore you have failed your fire test. Another one is structural collapse. So if the fire has gotten to your actual joists and structure to the point where it can't support its own weight, and it actually has as a like structural degradation, that's another failure. One that was more surprising to me is excessive temperature. So when they're doing this test, they increase the heat in that source room according to this curve here on this graph here, and then they actually measure the temperature in the adjacent room. And at first I was like, well, if it's just like really hot, like, but there's no fire, why would that be a failure? And what I've had explained to me, and maybe there's more nuance than I'm aware of here, but basically, if your firefighters need to enter that room to attempt a safe, like a life-saving procedure or whatever they're doing, and it's so hot in that room that their shoes are melting, then that's a failure, right? If they can't enter that room because it's too hot, then the partition has not provided the isolation for the fire that it was designed to. So that's why that would be considered a failure. And then this last one, number 4, is actually specific for walls. So we do it differently for floor ceiling assemblies and wall assemblies. But when you're testing a wall, you have this last thing where after the fire test is completed, you spray a fire hose at the test partition. And if that hose breaks through the wall, it's a failure. And that's got to do with the way that firefighters spray buildings. And there's a lot of nuance, I'm sure, to that I'm not aware of. But much like acoustics, you're testing a whole assembly. You're not testing one small part. So, right, like in acoustics, we often say no resilient channels don't have their own STC or IIC rating. They have a rating in the context of a whole assembly. So much like that, fire ratings apply to these whole assemblies, not just to one element of it. So the devil is in the details. Fun little analogy here to mushrooms. If you're just going in willy-nilly and grabbing mushrooms off the forest floor and eating them, not paying much attention to the details, you could find yourself in a tricky spot. And if you're gonna go willy-nilly and pick acoustic ratings and wall types and UL designs willy-nilly, you could also find yourself in tricky spots. So just a fun little analogy there. The devil is in the detail, acoustics. So this is kind of an interesting exercise where you can compare 3 wall types that all meet STC 50. And so, like we were mentioning earlier, STC 50 is the criteria for multifamily. It's pretty common across other requirements and codes and design guides. So STC 50 walls you see often. All 3 of these walls achieved STC 50 in an acoustical lab. So they would all meet the code, right? But are they really all the same? Can we go a step deeper? And us as acousticians do this often. We go deeper and we look at the actual 3rd octave band data. So what you're seeing here is a graph of all 3 of these walls. And then if you're not familiar, STC is based off of transmission loss. So you can break up how much sound has passed through a wall according to each frequency. So kind of like how much low energy passed through the wall and how much high frequency energy passed through the wall. And then you can graph it here. This is something acousticians do all the time. And you can see, okay, yeah, they all got this same single number rating, but if you look at it, they're all pretty different. And that green wall, the big heavy block wall, performed a lot better at the low frequencies, to the tune of 10 to 15 to maybe even 20 dB better. That's significant at low frequency. And then that double shear wall, the blue one, performed much better than the rest at the high frequency. So if you're just putting in these walls anywhere you need an STC 50 wall, you could run into some issues, right? If I have a unit, like a living unit next to a mechanical room, I might want to be blocking a lot more low frequency energy. And so as designers, we need to be thinking about how walls are appropriate for the spaces we're designing them to be in beyond just a single number rating. Because even though we could still hit these 50s and hit the criteria, we could still end up in that situation where a large percentage of people are annoyed in the space that they live in, which nobody wants, right? And also, we have another AIA accredited course called Better Design Details for Walls, and we go into this even a little bit more there. So if that's something that's interesting to you, reach out and look at our website. We've got that there for you. Kind of similar idea here, just for floor ceilings. So this, instead of STC, we'll look at IIC because that's unique to your floor ceiling assemblies. So these all achieved IIC 60, which is relatively good performing assemblies, but are they all the same acoustically? Again, the answer is no. There's less spread here, but that's not to say there couldn't be more spread. You know, you can have a million different walls that hit STC or IIC 50, 60. But you can still see there are differences, right? There's some interplay at the low frequencies and quite a bit of spread at the mid to high frequency. So if you know what your sound sources are going to be, and where kind of the sources of annoyance in a apartment building or condos or whatever it might be would be coming from, you can go a step better, go a step further and design a little bit better, using more than just your single number ratings. So similar to that is kind of the fire side. All three of the assemblies you see here on the page have met UL U465, which is a design for a fire rated wall, and they're all slightly different. So there's differences in the stud spacing, and kind of that top right one is a lighter gauge 19 mil steel stud, and then the one on the bottom is 97 mil, so quite a bit thicker steel studs. This would be something you'd see in more of a load bearing type of wall. And then the one on the left there also meets the minimum performances, or the minimum requirements provided by the UL design. So if you just are trying to meet the fire side of things and not thinking about acoustics, you can see here the spread is 38 for your STC all the way up to 64, which is very, very significant. That is orders of magnitude difference in perceived sound coming through that wall. So we can't just take the UL design and not be thinking about acoustics either. And just to complete the kind of analogy here, it's the same for your floor ceiling. All three of these meet that UL. In this case, it would be the L546 for your fire rating for your floor ceiling, but they're all designed a little bit differently, different types of clips, different, installations and all those sorts of things. And you get different acoustic ratings, like quite significantly. Again, in your IIC, you have 40 to 70, so 30 points different here, which is, again, significant. So tensions in the design team, all of these, everybody's got a little bit of a stake, right, in the design overall, and everybody wants different things when it comes to each different topic of discussion. So just as a little exercise, we've broken this into, we've picked these four relevant types of categories. So resilient element spacings, this is your RC channels or your clips and hat channels. Excuse me. Layers of gypsum board, pretty self-explanatory. How many layers of drywall or gypsum board do you have on your assembly? Stud spacing, again, pretty self-explanatory. And then screw spacing, which is specifically referencing how the spacing of your screws screwing in your gypsum board to your studs. That spacing is what we're talking about here. And then we have four involved parties, and we'll see how they feel about each of these topics. So kind of left to right up top, you have your developer, so the one that's paying for everything, the one with the money. Then next to them, you have the structural engineer. And then next to them, you have your fire protection engineer. And then maybe we should have put like a little sound level meter on this last person, but that's the acoustician. So how do each of these people feel about each of these topics, starting with resilient element spacings? Well, the person that's paying for everything is going to want wider spacing, right? Because if you go wider spacing, you use less material overall and less labor to install it, and that's a big cost saving. So the wider the resilient element spacings, the better when you're coming to pay for things. Then the structural engineer wants your narrower spacing, right? You have If you space things narrower, you have more points of tension that are holding things together, and that's better for your structural engineer. They might have less of a stake in, your gypsum board to your studs, that level of construction, but generally, kind of as a rule of thumb for them, they want more attachments and more stiffness and more structure everywhere. Your fire protection, they also want things narrower, right? Because as a fire is interacting with the wall or the ceiling, whatever it might be, things start to crumble. And there's, as your gypsum board, actually what's, I think, physically happening, I'm no chemist and I'm no fire protection engineer, but there are trapped water molecules in your gypsum board that interact with this crystal structure that give it some rigidity and some stability. And as it's heating up, the bonds there break and your water evaporates out of it, and that leads to crumbly gypsum board. So if you've ever seen gypsum board after a fire, you can like poke it and it kind of becomes dust. And so that's no good, obviously, for fire or for safety. And so because of that, they want things attached more frequently. So you want narrower, resilient element spacings. And then acoustics, that's us, or me at least. We like things spaced wider. The less attachment points, the less stiff things are, the more flexibility you have, and that leads to better sound isolation. Again, as just kind of a general rule of thumb. There can be some more nuanced discussion there as well. So layers of gypsum board, again, the person paying for it is going to want fewer. The less they're paying for things, the less material you're using, the better for them. So pretty obvious there. Structural engineers tend to want fewer layers of gypsum board as well. And you can imagine if you have a big tall building with, dozens of floors, and every wall's got either 2 layers or on one side or 1 layer on every side, you're changing the mass of your building to a point where it's starting to matter to the structural engineer. So maybe for some of your like smaller buildings, they don't care as much, but certainly as things scale up in size, they want less mass in the building as overall. Fire protection, they want more, because again, you just have more gypsum to try to evaporate all that water out of, right? If you double your gypsum, you kind of, not exactly, but you double the amount of time it takes for fire to deteriorate all of it. So more is better for fire. And then acoustics, again, we want more mass is better for acoustics, harder to kind of, like your sound has to interact with the gypsum panel. And if you have double the mass, it's harder for it to vibrate it. And so less energy transfers overall. Stud spacing, again, the person paying for it is going to want less material. So the wider the spacing, the less studs you use, and then the less labor to put up all the studs. So wider is better when you're paying for it. Stud spacings for the structural engineer, narrower is better. More stiffness, more attachments, kind of the same idea here. They want more of it. So narrower is better for them, and the weights tend to not be all that significant when you're looking at your whole building. So adding some studs is absolutely something they'd want to do. Fire protection is again narrower, more attachment points, better for fire. And then acoustics, we want wider as well. That is again less stiffness, less attachment points, less connection points for the acoustic energy to kind of travel through, leads to less transmitted energy. So less sound on the other side of the wall. Screw spacing, the person paying for it's going to want it wider again. Less screws saves a little bit of money, and every little bit counts, right? So you'll see that sometimes on your what do they call it? The VE effort sheets, like in the less screws they use, you can save a little bit here and there, and it can really add up. Structural engineering, they care less about screws, right? The mass is pretty insignificant, and as long as it's hung up on the wall, they're pretty much fine. That's not a big consideration of theirs. but they might opt for narrower just to give things more rigidity overall, but they have less of a stake in this one. Fire protection, again, narrower, more attachment points, better for fire, harder to crumble up your whole wall. And then acoustics, we want things spaced wider, less attachment points, less energy transferring through your system. So that's kind of where everybody falls on this. And I know we've only picked 4 different topics of discussion here, and in a real project, there's thousands. But as a former acoustician, former acoustical consultant, a lot of the recommendations I end up making or used to end up making on a project would increase costs. So there was always this conversation of, why do you want to do that? Is it really worth the money? Like, it's not my money, but I'm the one recommending it. And so I have to kind of fight for that justification. But if you look here, we actually end up agreeing with the developer 3 out of the 4 times. So I kind of had this feeling like everything I do is adding cost to a project. And that's not fully true. I mean, it certainly can be, and there's expensive acoustic upgrades you can do to buildings, but that's not always the case, which was kind of encouraging to see. So if you feel that way, rest assured at least a little bit. So rules of thumb can be dangerous. So a rule of thumb you'll often hear in acoustics is, and this is something I've said plenty, adding insulation to a cavity of a wall or a ceiling is good, but only up to a point, right? So if you're going from no insulation to having insulation, you get quite a big benefit. And then after that, you kind of get diminishing returns is how I often said it. So kind of some data to back that rule of thumb up here. You go from this empty wood joist floor ceiling structure to 90 millimeters of insulation, and you get an additional 8 points, both in STC rating and in IIC rating. So 3.5 inches of insulation, pretty standard. You get 8 additional points in both of your acoustic ratings. So that's a huge win. Insulation's a pretty easy one to talk people into adding. So that was a very common acoustic recommendation I would make. So, but then people would say, well, can we just fill up the cavity with insulation? And if that was so good for acoustics, why can't we just do it again, right? There's more space in that cavity. Let's fill it up. And that's not exactly how it works. You go from 90 to 270 here in this example, which is a little bit overfilled, but that's okay. You only get an additional 1 to 2 points. So you've added a lot of material now, and you're not really seeing that big benefit. So it's a little bit of a waste of effort, waste of labor, and there's probably easier ways to get 1 or 2 extra points for your structure. But if we just took that rule of thumb and applied it to all, we could find ourselves in trouble. Here's a thicker, like a much deeper floor ceiling assembly. And you can see here, if we go from 90 to 456, right? So it's deeper, that's quite a bit more insulation. We actually get an additional 3 to 5 points. So 5 points in your STC, 3 points in your IIC. So all of a sudden, if you're in a situation where you have this assembly and you're really trying to get 3 to 5 points, maybe insulation is a good option. And if you had just kind of taken that knowledge of, well, you get diminishing returns and thought no more about the situation, you could be missing a viable option here. So with that exact example, there's a whole nother consideration to layer on top of that, and that is the fire side of things. So the acoustic side of things, kind of self-explanatory, or at least acousticians have probably thought enough about all that to have a decent understanding of it. But there's really an interplay between your fire and your acoustics. So a similar assembly here meets your UL 587 fire rating. And you can see here up on the top left, this is a version of that assembly with no insulation, and your resilient channels are spaced 24 inches on center. Then you want to do that thing that we love in acoustics and add 3.5 inches of insulation. But if you look at the UL design, if you do that, you have to reduce your resilient channel spacing from 24 inches to 16 inches on center. So like we had said in that little graphic, acoustics wants things spaced further away, not closer. So we've added insulation, but we've reduced our spacing of resilient channel. So what does that do acoustically? We'll get there. Another option that comes up from time to time is laying your insulation just directly on top of your ceiling. And if you do that, according to this UL design, you have to reduce your spacings to 12 inches on center. And then if you wanted to go that next step and fill the void, fill the cavity with insulation, you again have to reduce to 12 inches on center. So there's a lot of variation allowed in UL design, and there's a lot of if you do this, then you have to do this. And you have to understand how the UL design is intended to be built and all the different options that are available to you. And it's a little bit more of a nuanced understanding of how things are designed and built. So if you haven't read a UL design, here's what you're missing. You're missing a lot of reading. This is section 5, bats and blankets in that same UL design we were just referencing. And here's the, if you do this, you have to do this. If you add 3.5 inches, reduce to this. If you add 3.5 inches on the ceiling, reduce to this, right? And times a million as you're reading through these. This is just section 5 of many sections. And it can be a little bit overwhelming. And so you will often find your resilient channel spacings here in this bats and blankets section, but it can also be in your gypsum section, which is a whole different section. And it can also be in its own section. And sometimes those sections will disagree with each other. And that's always a fun trick to try to resolve. So if you find yourself in that situation using PAC products, feel free to reach out. We'd love to help navigate that with you. So let's talk about kind of combining those, your insulation and your resilient channel spacing. So at 24 inches on center spacing with resilient channel, sorry, real quick, on the left side, we have the differences as you change your RC spacing. And then on the right, you have your differences as you change your insulation thickness. So we can kind of use this to compare both variables at once. You add your 3.5 inches here and you get an additional 8 points, right? That's what we had kind of talked about. But as we said, if you increase or if you add your insulation to 3.5 inches, you have to reduce from 24 inches on center to 16 inches on center. So you get 8 points for adding insulation, but things are spaced narrower, which is bad for acoustics. So you actually lose 4 points there. So your net benefit, right? If we had could just take these general rules, which again can be dangerous, but we'll do it for here at least. You net 4, right? So that's not as good as you had maybe hoped it would be. And then you say you want to go that extra step of adding, filling up your whole cavity. So you go all the way up to 270 millimeters of insulation, and you get an additional 1 point for that full cavity. But again, you have to drop it all the way down to 12 inches on center for your resilient channel spacing, which at least in the IIC here didn't make a difference. So you gain 1 point ultimately for that. But not only are you increasing your thickness of your insulation, you're also increasing this or decreasing, sorry, the spacing of your resilient channels. So it's more parts and labor on two fronts now, which again, that developer is not going to be stoked to hear. And if you tell her, hey, it's all for 1 point in acoustics for your IIC, that would be a hard conversation to have. So maybe it's necessary. I'm not saying it's never necessary, but you have to at least be ready for that conversation. So again, increase your insulation, you increase your isolation. But that also, if you're following a fire design, that means you're reducing your RC spacing, which is reducing your isolation. So you have competing effects happening at the same time. So these rules of thumb can be very dangerous, and it gets very complicated very quickly. So what do? You ask the experts, and we would quickly refer you to an acoustical consultant once things get that complicated. And you can find acoustical consultants on these two different directories, and there's a couple other directories you could find out there with acoustical consultants. but this is what they are kind of thinking about on their projects. Okay, so yeah, another example of acoustics and fire, kind of from the fire side of things. On a wall, both of these studs, and both stud gauge and stud spacing is the consideration here, but both of these walls meet UL U465. But you'll see the stud gauge is specified as a minimum, and so is the stud spacing is specified as a maximum. So both of these walls meet that UL U465, but have different stud thicknesses and different stud spacings. And you can see there's a 10-point difference in your acoustic rating. So just because you're meeting I think a big takeaway is you can't just say UL 465 equals STC 48, right? There's a lot of different ways you can build that assembly and be okay on the fire side of things, but not be okay in the acoustic side of things. Another tricky one that comes up from time to time is your 2-hour floor ceiling assemblies. And so when you're dealing with these 2 hours, right, like most of the things we've been talking about are to reach 1 hour. To reach 2 hours, you have to go a few steps further to make things a little bit more fire resistant. So what you often end up getting is what we call an RC sandwich, and it's famously bad for acoustics. You have a small little air cavity with resilient channels in it, and that's here. I think you'll see it on the next slide here. Yeah, so it's not ideal acoustically. Up top, you can see just a standard floor ceiling assembly with a resilient channel. And then if you try to follow that 2-hour fire design and make your RC sandwich, we've dropped our STC and IIC ratings by about 15, which is a big deal. Nobody wants that. So you've added mass, right? Going from this top one to the bottom one, but the way we've done it is bad acoustically. And so even though we like more mass in acoustics, it's also if you have to do it the right way or you can find yourself in trouble. But comparing it to a floor ceiling without the insulation and without the extra mass and without the resilient channel, it is still an improvement, but it's just not nearly the improvement you could get with the same amount of material and effort. And that's just kind of the nature of these 2-hour fire rated designs. It can be quite tricky to design for both 2 hours of fire resistant assemblies and acoustics. So what's the solution? We'll get to in a second here. But these things do happen, right? There's projects where you have like a restaurant, especially in some of your bigger cities or city centers, you have restaurants on like the floor layer, and then like apartment buildings above that. And often there you need a 2-hour fire rating. So in those situations, these restaurants can be open quite late and have live music, and you have families trying to sleep above, and nobody wants screaming kids in the middle of the night or in their middle of the night, which is just late dinner time or something like that. So what is the solution is you kind of have to end up treating, or at least an approach we've taken often, is you treat the two parts of the assembly different. So you go ahead and you use your sub-performance acoustical assembly for the 2-hour fire rated design. You can see the RC sandwich there, and you just add on your acoustics upgrade, right? So the top bit here meets your fire rating, and then you hang an additional ceiling. Excuse me. Here is shown on spring isolators for the acoustic side of things. And so that's another conversation you'll have to have. That's a rather expensive upgrade. And springs are kind of come with their own host of complexity and issues to a project. It also requires a lot of vertical space. Here's another option that's a little bit thinner. You have just clips instead of springs, really. But it's not as good acoustically because we now are dealing with a smaller cavity. And so there's a trade-off there, but you gain some of your vertical height back. So the pros and cons, depending on which way you go with that. You can also, of course, add it to the top side. Here's just kind of a floating floor. So you have your 2-hour fire rated assembly, and then you add acoustics to the top. So another example here, checking the time, make sure we're good. Yeah, we're pretty much on track. Wall-to-wall intersections. So you'll see here you treat wood stud construction and steel stud construction a little differently. It's a little easier with your wood intersections. If you have your fire-rated wall between your units and your corridor, and you want to intersect them with a wall between units or between two of the same units, like demising wall, you can use wood blocking to interrupt your gypsum board, and that's allowed by your fire design. So if you kind of trace the paths, you have your fire rating met in every direction you need it to, and you have your acoustical. Mostly there's like a little bit of a flanking route if you kind of go diagonal, but that tends to be a pretty lossy connection and tests all right acoustically. So you can meet both requirements there that way. And then if you have a fire rated wall, right, so you're between two different units, you can basically follow the same process here and interrupt your gypsum board with your wood stud blocking and be okay for both fire and acoustics. And you have your resilient elements in every direction that you need them, and you're all right. It gets a little trickier though when you're dealing with steel studs. So you cannot use steel studs as blocking for fire. So you have to kind of come up with a different approach. So if you have a fire rated wall intersecting another fire rated wall with steel studs, an approach we've often detailed out is intersecting it and going all the way through. So you have a more robust system kind of in every direction you could kind of draw between your additional or your adjacent units and corridor that all meet the fire rating. It's a little easier, again, if you're going unit to unit where you don't have to meet that same fire rating. You can just butt it up to the fire rating wall. But that does give you this acoustical flanking path where you don't have nearly the mass there. You just have two beads of acoustical sealant. So if you are worried about your unit 1 to unit 1 like acoustic transmission path, like say you have a bedroom next to like a home studio where you're trying to record music or something like that, and you want this to be acoustically robust, you have to actually upgrade this to a fire rated wall, because then again we're going back to this system where we penetrate all the way through the wall, but you can't use steel studs as fire blocking. So this wall has to be fire rated as well to meet all the requirements of breaking this wall. So it gets very tricky there, right? And now all of a sudden this wall that goes unit 1 to unit 1 is fire rated, which adds some complexity to it, and it limits the materials you're allowed to use in it. And you have to look at the UL design and follow all the requirements they specify there. You also have to get it like inspected more. So it just becomes a little trickier. So wood walls to ceiling intersections, again, with wood, it's somewhat straightforward. There's lots of details. And again, we have another AIA presentation where we really dive into some of these details. But you can use your wood blocking to interrupt your gypsum board. And it's not too hard to detail this out. This gets a lot trickier with steel studs, which go watch our other webinar, call us if you have questions about that, because that's a bit of a longer conversation. So tensions in the design team, what's good for fire is not always good for acoustics, and vice versa. And if we're not thinking about each other, we can come to different conclusions that make things trickier for everybody involved. So just a question, who on your project team is typically responsible for coordinating the fire and acoustical details and how they interact with each other? I think typically I've seen that fall to the architect, which then requires that the architect is knowledgeable about both acoustics and fire, which is, I mean, there are certainly those out there that are, and that's great for them, but they have many, many other things to be thinking about, and they can't know the acoustics side as good as an acoustician, and they can't know the fire side as good as your fire protection engineers. So how does that work out on your projects? And then just another quick shout out to Maxon and Pabco. When this presentation was first done, it was done with Mike Rayleigh here from PAC and the help of Evelyn Way at Maxon and Ben Schaefer at Pabco. And then a lot of the data presented here was from the National Research Council of Canada. That's where you saw a lot of those iterations of RC spacings and installation spacings. And the Institute of Noise Control Engineering helped put on the first version of this. So just shout out to all of them. Any questions? We'll sit on and take some questions. I think Mike Rayleigh will pop back up.
Yes, I'm here. I have seen nothing pop up in the Q&A. Excuse me. So it seems like you answered all of the questions. I see a comment that says, I've yet to meet a fire protection engineer that knew more than an architect about passive fire protection. Interesting.
Yeah,
I do see that somebody's got a hand raised.
Samuel.
Looks like, let me allow the mic, and then you can, Samuel, you can unmute yourself.
Gentlemen, can you hear me?
Yeah, we can now.
Yeah, I apologize, but during the whole presentation, I could not submit a question on the chat. So when you were doing your presentation, I couldn't send a message or anything.
Interesting. It looks like others have been able to, so maybe there's just, I think everybody should have that same access, but who knows how these things work sometimes. Yeah, it could just be
that
Teams.
was my only question at the moment.
I see Dave sent a test. We might have different permissions on the presenter side too.
No, other
we'll make sure we get that checked out as well.
So. Yeah, we'll take a look.
Thanks, Samuel.
Thank you.
Any questions, anybody? You know what, Drake? I've got a question for you. Actually,
all right,
now,
hit me.
I'm gonna put you on the spot. You know, like you were an acoustical consultant for several years, and you know, I was an acoustical consultant for 10 years, and there are definitely things that I would do differently now. Where I'm an acoustical consultant with what I've learned about construction and fire. I'm curious what sort of comes to mind for you as you're still kind of new and getting into this. What would you have done differently, either slightly or significantly differently, when you're a consultant?
No, that's a great question.
Looked more at fire.
Yeah, and I've talked to a number of acoustical consultants, and I don't know. I think this is somewhat universal. I think we see UL listed on a partition type sheet, and we're like, great, moving on, and put no additional thought into it. I hadn't read a single UL design. But then I would feel free to go mark up those partition types and be like, hey, the changes you have to do are decrease the stud spacing here, decrease the stud gauge here. And I didn't think about the UL part of that at all. And it would just, I think the easiest thing in the world would have been to just have a note that said, verify this is allowed by the UL design, because I can see that the UL design is written right there. And at least that's calling attention to it, and it's not putting the burden on me. Or I could have gone a step further and know what is allowed in the UL design, which probably would be the best practice, and make sure the things I'm recommending can actually be built and actually pass fire inspections. I think back to my time as a consultant, and I remember this one project where I had a door that had to meet a ballistic rating and an STC rating, and I had to go find a door to do that. And of course, I took into account both ratings. I don't know anything about ballistic criteria, but I figured out enough to know that I'm recommending a door that meets the ballistic requirement because I knew it existed.
Right. Yeah.
You know, and I said, verify with the manufacturer or whatever, but this one seems to meet both. I should have been doing that for the fire rated partitions I was marking up as well.
Yeah, same. I see Andy's got a question. Andy, you should be able to unmute yourself now. I think Mike is allowed for you. And actually, I think I can just do. Can I do that for everybody? Yeah, Andy, I think you can unmute yourself. Your mic is allowed. If it's not working, you can put a question in the Q&A. Oh, I just see Andy says, is this presentation info available Yes, the presentation is available. There's a recording of it on PAC's website. Mike or Taylor or Dave, if one of y'all has that link up, if you want to grab that link to our webinar page, you can go see there. We have a recording of this AIA presentation and our other AIA presentations, along with other webinars as well that we've done.
Looks like he added a comment. What are the best sources for UL and STC standard details similar to the exhibits you used in this presentation? I mean, we at least have our manufacturer, like we're the manufacturer, right? So if you want to use our products, we have plenty of details, and you can reach out to us and we can walk you through those. I don't know that there's like a database anywhere out there that puts together details like this for just everything, like competing manufacturers and stuff like that. But if anyone knows of any, feel free to throw them in the chat. Mike, did you have anything else on that?
Well, no. So one of the things that go ahead, Mike.
No, go ahead.
You say one of the things that I've run into a fair bit is, people wanting things that combine both the acoustics and fire, and shows that like this acoustical assembly also actually complies with this fire rated thing. And some manufacturers like PAC, we've really tried to, and over the years as we've learned more and more about fire and acoustics, tried to make sure that whatever we go test acoustically also is being built in accordance with at least one UL design, usually many UL designs, because we have our products in a whole bunch of UL designs. And there are we're not the only manufacturer that does that, but not all of them do that and try to align the acoustics and the fire either intentionally or unintentionally. But the Gypsum Association, I think somebody responded with that, the GA Fire and Sound Design Manual, that's kind of the one somewhat independent. I mean, it's still an association of a bunch of manufacturers, but it's not just one. But that's kind of the one entity that I'm aware of for kind of typical assemblies that tries to combine acoustics and fire. Now you still have to look at, they'll have the fire design, and then underneath it'll say for sound test, and it'll give you some additional specifics of that. And you really need to pay attention to that. And if you're using that as a reference and you're using older versions, I would very strongly encourage you to get one of the more recent copies, because they have made a lot of changes to it. They've gotten rid of a lot of old assemblies. They've gotten rid of a lot of assemblies where the acoustically tested assembly that was referenced didn't actually meet some of the things with the fire rated assembly. I think there's actually one or two assemblies that I've gotten taken out of the GA manual because the acoustics reference. There was an old NRC test, like the screw spacing that they used to attach the drywall to the studs or the resilient channel didn't actually match what was required in the UL design. So if you get a more up-to-date copy, they've addressed a lot of that. Somebody mentioned the mass timber one. That tries to look at fire and acoustics too. So there are some sort of like broader industry references out there, but it is tricky to try and combine both of those. There aren't many resources that do it.
Even with that, you still have or should reference back to the UL design to find out what the final spacing really needs to be. I know in the GA, in some circumstances, sorry, this is Mike Gernhardt. I'm the fire kind of expert here, if you want to call it that. Even the GA will reference back to a UL design, and so you have to cross-reference the acoustical test that is stated on the GA design to the UL assembly and make sure that your scenario fits both test correctly, because the test may be published with the insulation up against the top side of the plywood, which allows you 16 on center, but your customer or your client wants to lay the insulation across the back, which makes the channel at 12 inches on center. So there are some minute details that still get in the way of creating a one source, wholesome, fully encompassing fire life and safety and acoustic manual.
Yeah, that's totally true. And there's also, like this particular product may only be allowed with these other products within the assembly. There's some restrictions on what you can use together and can't use together with those in those assemblies that the necessarily limited listings in the GA manual don't fully capture. Here's another one from Brett. How do you determine the ideal spacing of the resilient components of a floor ceiling? So 16 inches on center versus 24 inches on center, for example. If you have a relatively heavy finished ceiling, such as T&G wood planks, being attached to or through the fire-rated assembly, since too tight spacing of the RC hat channels can defeat the resiliency of the system. Do you factor the overall weight of the assembly?
Yeah, I think you've got a couple of variables there. And probably like first thing you'd have to nail down is what is the expected level of sound transmission through this partition? Do you have to meet any specific requirements? And then kind of like we were talking about for acoustics, the wider the spacing of your resilient channels, the better. So if you're trying to meet something a little bit harder, you might have to go find a test that shows that. One of the mics could probably jump in here, but for actually like supporting a heavy finish, resilient channel has like maximum weights it can support based on its spacing, and that might become a factor that gets in the way of your design. Yeah. Any other thoughts?
Yeah, I would say, yeah, I mean, so you have a number of different things that you have to balance, right? So if this is, it's obviously it's an acoustical assembly. That's what we're talking about here. So you want to try and optimize for acoustics, which means wider spacing, like Drake said. If it's a fire-rated thing, then you also need to optimize for fire, which means narrower spacing. And then you also need to optimize for holding the weight of all of the layers, which is going to mean narrower spacing so that you've got more structural support in order to carry the load. So you have to find sort of the optimal balance between all of those. And so, really it's look at what is the maximum that's allowed for both, the load bearing capacity and also for fire, figure out what the maximum is, out of that, and then do that because that's what's going to be preferable acoustically. I will say that with these kinds of things, like, so resilient channel, what is it? Ceilings, they say you can, what does Dietrich say? Ceilings, you can usually do 2 layers at 16 OC, I think is typical.
Yeah,
but I mean, it depends on the
typical
fire rating and stuff like that. I think that's what their install guide says. It's been a while since I've looked at it. And some resilient channel manufacturers will have different kind of guidelines for spacing and number of gypsum board layers. But if you're going to attach another layer to that, maybe you've got a 2-layer ceiling and you're going to attach T&G wood over that, that's additional load. So you would need to probably reduce your spacing. I will also say that trying to screw those wood planks through and attach to resilient channel, that's just another set of screws that could short circuit it, right? That's maybe a different contractor installing your T&G wood planks that's maybe not as familiar with installing to resilient channel. So you just have even more opportunities to short circuit resilient channel, which is really common in practice. And so that's where I would say really use Risit clips because you have more flexibility. There's also the hat channel has a little bit more load bearing capacity to it than the resilient channel, just because it's got 2 legs and you're not getting the isolation from just a flimsy piece of steel. You're getting the isolation from the rubber isolator in the Risit 1. And it'll be a little bit easier to just build it and construct it. And those are the kinds of things where, reach out to the manufacturer of the products that are going in the system and work with them to make sure that, what you're doing is optimized for load, acoustics, fire, all those kinds of things. And that's, that's why PAC does this. That's why we're here, so that you can reach out to us and we can help you work through those things, because there's not a one size fits all answer for these.
Yeah, and just as a cautionary tale with resilient channel, again, even if you go to, let's say, Dietrich or Semco's website and you pull off their load capacity for the resilient channel, be sure your specification is very clear that there are no exceptions, no variables allowed, because every manufacturer has a slight variation in the resilient channel and the type of steel they use and the thickness of steel they use. So even though, one manufacturer may say you can hold X number of pounds per square foot at this spacing, it doesn't necessarily mean that's what's going to end up on the job site. So as I ran a drywall supply yard for almost 20 years, and very seldom did we care what brand of resilient channel we had. We always just bought the cheapest thing we could get our hands on because that's what our customers need fit. So just as a secondary cautionary tale, if you're going to go through the details and specify a brand specific item name, make sure that that's what ends up on your job site.
Definitely. Yeah. Any other questions? Questions, comments, topics of discussion, anything like that? If not, that is the end of our presentation. We've done everything. Like we said, Taylor's email is in the chat at the beginning. It's just taylor@pac-intl.com. If anybody needs credits or a certificate or anything like that, please email Taylor. She'll get you taken care of. Stay tuned for our next webinar. Like I said, Drake is going to continue doing these. I'm not sure if we have one scheduled yet for next month.
I don't think it's on the schedule yet, but it probably will be soon.
Yep, should be soon. So we'll do that, and we'll redo some of the many webinars that we've had. We have, I think, 4 AIA accredited webinars, and we have a bunch of other ones that aren't AIA accredited, but are still certainly useful information. So I think Drake will keep going through those, and then start working on his own too, adding whatever makes sense to him, and probably some new things on mass timber and additional things as we get going. So when Drake asked about like where do you go get your fire ratings or your acoustical ratings, we do have that on our website. So we have our assembly selectors. If you just go to the PAC International LLC website, pacinternationalllc.com. I'll stick that in the chat here. Then we have at the top, there's some PAC assembly selectors. We have a UL fire rating selector that you can go to. Go find, you can look for specific PAC product and see what UL designs it's in, or you can go look for a specific UL design and see what PAC products are in it, or you can look at, a general structure type like solid wood joists and see kind of what UL assemblies there are that include PAC products, so you can kind of filter it down that way. We also do have an acoustical rating selector. That one we do require you to register, just name, email, this kind of stuff. But you can get in there and also filter down through the different assemblies there to try and find what you're looking for. So those can be really helpful tools.